Green's theorem. Let R be a simply connected plane region with boundary a simple closed piecewise smooth curve C oriented counterclockwise. If f of xy, g of xy are continuous with continuous partial derivatives on some open set containing R, then the line integral over C f of xy dx plus g of xy dy is equal to the double integral over R of the partial of g with respect to x minus the partial of f with respect to y dA. The most important part of this theorem is in red here. Very often you'll be asked to compute the line integral over the curve C, and the double integral over the corresponding region R might be easier to compute. Although sometimes you may want to do the computation the other way as well. Sometimes you could be given a double integral over a region, and you may want to change it to a line integral over a curve. Now, as I said, the part in red there is the most important. All of the text that is written before that are the technical details that are required in order for the theorem to be applicable. But let's just go through some of the terminology used there. When we talk about a simple closed curve, well, a curve is closed if its starting point and ending point are the same. And a closed curve is simple if it does not intersect itself. A curve is smooth if there is a parametrization R of t of the curve such that R prime of t is not the zero vector. And a curve is piecewise smooth if the curve can be split up into finitely many smooth pieces. Let's try an example. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. So the example says, evaluate the line integral over C, x squared minus y squared dx plus 2y minus x dy, where C consists of the boundary of the region in the first quadrant that is bounded by the graphs of y equals x squared and y equals x cubed. Before we begin, let me just mention that that notation on the integral, that circle with an arrow on it, is to indicate that the curve is a closed curve oriented in the counterclockwise direction. The circle tells us it's a closed curve, and the arrow tells us the orientation. So we should always start by sketching a picture of the curve. Here I have a picture. You could see I've sketched the graphs of y equals x cubed and y equals x squared. And as I've stated, the problem is telling us that we should be moving in the counterclockwise direction. So we move left to right along x cubed, and then right to left along x squared. The corresponding region is this shaded region in yellow here between the two curves. And we could change the line integral to a double integral using Green's theorem. We take the partial of 2y minus x with respect to x, and that just gives -1. And then we subtract the partial of x squared minus y squared with respect to y, and that's -2y. So just simplifying that, we get -1 plus 2y. We're going to do it as a type 1 region. That means that x is going between 0 and 1 because the curves y equals x squared and y equals x cubed intersect at the points 0, 0 and 1, 1. And y is going from the lower curve to the upper curve, that's y equals x cubed, to y equals x squared. Now we're ready to do this pretty straightforward double integral. We first integrate with respect to y to get -y plus 2y squared over 2, or just y squared. And we plug in the x squared and the x cubed and subtract. So we get -x squared plus x to the 4th minus -x cubed plus x to the 6th. And now this is just a bunch of power rules. We get -x cubed over 3 plus x to the 5th over 5 plus x to the 4th over 4 minus x to the 7th over 7. Notice I distributed that minus sign in the middle through, and that's going from 0 to 1. So plugging in the 1, we get -1/3 plus 1/5 plus 1/4 minus 1/7, which simplifies to -11 over 420. Plugging in the 0 just gives 0, so we don't have to worry about that. Let's try another example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the line integral over C, x to the fifth minus 3y dx plus 2x minus e to the y cubed dy, where c is the circle x minus 1 squared plus y minus 5 squared equals 4. Here's a picture of the given circle. Notice it's a circle of radius 2 centered at the point 1, 5. The corresponding region is the interior of that circle. We change the line integral to a double integral using Green's theorem. We take the function 2x minus e to the y cubed and differentiate with respect to x to get 2. And then we take the expression x to the fifth minus 3y and differentiate with respect to y to get negative 3. We subtract 2 minus negative 3 to get 5. We could pull the 5 outside of the double integral because it's a constant. Now the double integral over r dA is just the area of the region R. That's just the area of the given disk. So the area of that disk is pi times 2 squared. So we get 5 pi times 2 squared, or 5 pi times 4, or 20 pi. Let's try another example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the line integral over C f dot dr, where f is the vector field negative 16y plus sine x squared I plus 4e to the y plus 3x squared j, and C is shown in the figure to the right. So notice that C consists of 3 curves, y equals x squared plus y squared equals 1, and y equals negative x. The corresponding region is shown in yellow there. We're going to change the given line integral to a double integral by taking the partial of 4e to the y plus 3x squared with respect to x to get 6x, and then subtracting the partial of negative 16y plus sine x squared with respect to y to get negative 16. And when we subtract, we get 6x plus 16. It looks like this one will be easiest if we do it as a polar region. So notice that theta is going from pi over 4 to 3 pi over 4, because the line y equals x is at a 45-degree angle from the positive x-axis, and the line y equals negative x is at a 45-degree angle from the negative x-axis. R is going from 0 to 1 because it's going from the origin out until we hit that circle of radius 1, x squared plus y squared equals 1, which in polar has equation r equals 1. We replace x by r cosine theta, so we get 6r cosine theta plus 16. And as always, since we're changing to a polar double integral, we multiply by an extra factor of r in the integrand. The integral itself here is straightforward, so I'll leave it for you to work out the details. The final answer is 4 pi. Go ahead and finish this double integral yourself and check your answer. Green's theorem for multiply connected regions. Remember that a region is multiply connected if it's connected, but it has some holes. So here's a picture of a typical multiply connected region with one hole. Notice that we have the outer curve traversing counterclockwise and the inner curve clockwise. We labeled the outer one C1, the inner one C2, and the corresponding region R. Okay, this is a multiply connected region with positive orientation. Okay, we say that it has positive orientation if the outer curve is counterclockwise and the curves around all the holes are clockwise. Green's theorem for multiply connected regions says that the double integral over R, partial g with respect to x minus partial f with respect to y dA, is equal to the sum of the line integrals. The first one, the line integral over C1 f of xy dx plus g of xy dy. And the second one is the line integral over C2 f of xy dx plus g of xy dy. Okay, so we add the line integral over the outer curve plus the line integral over the curve surrounding the hole with the correct orientations, and we get the appropriate double integral, the same double integral we had for the standard version of Green's theorem. Let's look at an example. Evaluate the line integral over c negative y over x squared plus y squared dx plus x over x squared plus y squared dy. The first thing to notice about this line integral is that it does not meet the requirements for applying the standard version of Green's theorem. The problem is that the curve is bounding a region that contains the origin, and the functions little f and little g both are not defined at the origin. So in particular, they can't be continuous there. So we can't apply Green's theorem unless we get rid of the origin. So that's your hint. Now, go ahead and pause the video, try this example yourself, then resume the video to check your answer with mine. Okay, so the first thing I'm going to do is I'm going to draw a little circle of radius 1 inside that square. Now, it doesn't matter what size circle we use. We could use any size. Obviously, the easiest one to use, if possible, is the unit circle, x squared plus y squared equals 1. So since that fits inside the square, that's the one I'm going to use. Notice I'm also orienting it clockwise so that it matches what we need to be used for Green's theorem for multiply connected regions. Okay, now we need to compute the two partial derivatives. The partial of g with respect to x, well, that's a quotient rule. So it's the denominator, x squared plus y squared, times the derivative of the numerator, which is 1, minus the numerator, x, times the derivative of the denominator, 2x, over the denominator squared, x squared plus y squared, squared. That simplifies to y squared minus x squared over x squared plus y squared, squared. Similarly, the partial of f with respect to y simplifies to y squared minus x squared over x squared plus y squared squared as well. So we have that the left-hand side of the equation for Green's theorem for multiply connected regions is the double integral over r 0 dA. And the integral that we're looking for is going to be equal to that minus the integral over the inner curve, which we've labeled as d, of the same expression, negative y over x squared plus y squared dx plus x over x squared plus y squared dy. Again, I just got that by solving the given equation in red there, the equation for Green's theorem for multiply connected regions, by bringing the term all the way on the right over to the left-hand side of the equation. Now, luckily, the line integral over d is much less tedious to compute than the line integral over c. For the line integral over c, we would have to do 4 separate line integrals and add them up. For the line integral over d, we just have to parameterize the unit circle. Before we go ahead and do that, I just want to mention a couple things. Number one, the double integral over r of 0 dA is just 0, so that goes away. And we can get rid of the minus sign in front of the line integral there by reversing the order of orientation. So we could change it to going counterclockwise and getting rid of that minus sign. So we get the line integral over d oriented counterclockwise of that same expression. Okay, now parametrizing the unit circle in the usual way, we have x equals cosine t, y equals sine t for t between 0 and 2 pi. So x squared plus y squared is just 1, so those denominators go away. In place of y, we put sine t, and in place of x, we put negative sine t, so we get sine squared t. And in place of x, we put cosine t, and in place of dy, we put cosine t dt, so we get cosine squared t. So that's where we got the sine squared t plus cosine squared t inside of our definite integral, and that's just 1. So we just get the integral from 0 to 2 pi dt, which is simply 2 pi. Green's theorem allows us to derive a few really nice area formulas where we use line integrals to compute areas instead of double integrals. First of all, we can replace f by 0 and g by x in the formula for Green's theorem. To get the line integral over cx dy is equal to the double integral over r dA. And as we know, when you don't put anything inside a double integral, or equivalently there's a 1 there, you just get the area of the region. Similarly, if we replace f by negative y and g by 0, we get that the line integral over c negative y dx is equal to the double integral over r dA, which once again is the area of the region R. So this gives us two very nice area formulas involving line integrals. Right, so just to summarize the two that we found, we could compute the area of a region by taking the line integral over C, where C is the boundary of the region, x dy, or we could do negative y dx. If we add these two area formulas, we get 2 times the area is the integral over C x dy plus the integral over C negative y dx, or equivalently, the area is 1/2 the line integral over c x dy minus y dx. This gives us a nice third area formula that can be used. Let's try an example. Find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. As a hint, this one will work out easiest if you use that third area formula, 1/2 the line integral over c x dy minus y dx. Go ahead and pause the video, try this yourself, then resume the video to check your answer with mine. Okay, we'll start by parametrizing the ellipse as x equals a cosine t, y equals b sine t. T goes from 0 to 2 pi. So according to our area formula, we have 1/2 the line integral over c x dy minus y dx. And changing that to a double integral, we replace x by a cosine t. We replace dy by b cosine t dt. We replace y by b sine t. And we replace dx by negative a sine t dt. And the integral is going from 0 to 2 pi. So we get ab cosine squared t plus ab sine squared t, which is just ab. And since ab is just a constant, we could pull it out. We get ab over 2 times 2 pi, or equivalently pi ab. This is the standard formula for the area of an ellipse.